Yeah, thank you. So today I'm going to talk about one of our papers called Theory-Independent Randomness Generation from Space-Time Symmetries, which is joint work with Caroline Jones, Albert Alloy, and Marcus Miller. All of this is part of a broader research project, which already Marcus mentioned in his last talk, where we try to build a framework where we can study the interplay of space-time geometry and the probabilities of events. We do this by extracting symmetries from the geometry of space-time, and then via group representation theory, we see what this implies for semi-device independent scenarios. Or we frame it in a more clickbait way. We put back the black box approach of quantum information into space and time. So this is what I'm going to talk about today. First, I will give you a short introduction into the semi-device independent framework. Then I will explain the exact setup of our random number generator, tell you a bit what was already done in the literature. Then I will tell you what we have done, present you our results first assuming quantum theory and then going beyond quantum theory. And yeah, finally I will give you a conclusion and an outlook what we will do next. So before we go to the semi-device independent approach, I will talk a bit about the device independent approach, which probably most of you have seen. It's just a bell setup. I will not go into many details because I think you're all pretty familiar. But what I want to point out here is that basically in this setup, we do not assume anything about the boxes. We only know to take inputs and create outputs, but we don't assume how the inner working is, like from which theory we assume in the first place. All we do is we study the probability distributions that we get in the end. And then we can try to see if specific correlations are compatible with specific theories. For example, like this, I think also everybody has seen this, which like if you have some correlations that are within this set, then we know there can be some classical mechanism inside the box that explains them. If you're in the blue area, then there's some quantum description. And like the most general ones are just non-signaling descriptions where like we only assume that you don't have any signaling between those two boxes. Okay, so this is very nice. We learn a lot about nature, but it's very hard to implement in the laboratory. It has been done, but it's very hard. So what people also are interested in are semi-device independent scenarios where we actually give up this restriction, this assumption that the two boxes are space-like separated, and we actually allow communication between those two boxes. And we will especially look at a specific scenario where Alice, the first box, can signal something to Bob. But if we don't make any further assumptions here, then basically we can create any kind of probability distributions that we want, even within classical probability theory. So that's exactly the reason why we go from the completely device-independent setup to some semi-device setup, where we will describe at least some parts, a bit more of our setup, and make some assumptions about them. So the first one is that we assume that basically all of this can be described by quantum mechanics. And the transmitted system is a quantum system. And now we can make assumptions about the transmitted systems. For example, we could say, okay, we bound the dimension of the Hilbert space. For example, we could say the transmitted system is always a qubit. This is also very hard to certify in the laboratory. So people thought about what could we do else. So what they did, especially in the von Himbeek paper here, is they said, okay, we have an additional observable, for example, the energy, and we bound this observable. So we say the transmitted system, the expectation value for the energy must be bounded, and then you can basically analyze the setup, and you will see that you can actually create randomness with the setup. The only problem with this is that this still relies on the validity of quantum mechanics. So here we assume that our measurements are POVMs, our system is really described by quantum state, and this is something where we want to be more general. We don't want to make these assumptions, but still want to certify randomness. So what we did, we looked at the following setup, which was also introduced by Marcus, where you have two boxes, and basically you can rotate the first box. And you have two different settings. So the first one is either you do nothing to the box, or you rotate it by a given angle alpha, which is arbitrary but fixed. And then we will make some assumptions on the system that is transmitted. So we say it has to be in some statistical response to our spacetime symmetry, in our case to the rotations. And we will basically make a bound on how this can behave under this rotation. And then we only consider here two output measurements. So first we will describe this within quantum mechanics, a bit as a warm-up and also to understand what's going on. And we'll define the set of all the correlations that we can find within the setup, where we have the two correlators, E of x, which is basically just the expectation value of some observable with two outputs, either plus or minus 1. So you could also read this as the probability of finding plus minus the probability of minus given for a setting x. And the states that will be sent depends on your input. So either if you input 1, then when you do nothing to the box, you will send phi 1. And if you rotate the first box, you send phi 2, and this is connected with this representation of SO2. And yeah, so this is also where our rotation comes in. And we can actually implement our assumption on the bound of, so we can bound the spin on this. So here we can say, okay, like our representation is of this form, and it's bounded up and below with some j, which is either an integer or a half integer. Yeah, so this would be just how the state would transform then. What is important here is, since we make this assumption on this upper bound, the state cannot be just like jump into an orthogonal state. So basically what you have here, phi 1 and phi 2 have to have some overlap. So they're not perfectly indistinguishable as long as j alpha is smaller than pi over 2. And this is basically the case that we will look at because this one is boring. There you have two distinguishable states, perfectly distinguishable states, and you could do whatever you want with that. So this parameter gamma here can be now used to give you the shape of the set up here. There are some results in the literature, and we use them, and then you can basically derive this form here, which tells you exactly that this is the shape of the quantum set. Yeah, good. To talk about randomness certification, we also have to know what are the classical probabilities that you can see. And basically, this is when our box either behaves in a deterministic way, or if we have convex combinations of so classical probability distribution over deterministic behaviors of those boxes, which will adjust this line here. And if you look at the definition, what I want to stress here is that the definition still depends on our definition of the quantum boxes, which is in the first place not a really good thing to do, but I will argue later that this doesn't actually matter, and we don't have to worry about it. Okay, so yeah, so far we only talked about pure states. In principle, we could define a similar set just using mixed states. As it turns out, that, we don't care if we work with pure mixed states, because obviously the set of pure states is a subset of the mixed states, but also the other way around is true. We can use some purification argument where we purify in a way that we don't pick up any additional spin, and therefore we see this is also a subset, and therefore both of the correlation sets are the same. Yeah. And what we also did is we looked at this set here, which we called the relaxed quantum set, where we wanted to grant some room for experimental errors. Maybe this form is not very enlightening, but you can actually rewrite all of this in this form. And this has a nice interpretation. Basically, what we are saying is we trust, for example, with a probability of 90% that our assumption holds, like our bond of the spin. And in 10% of the cases, we don't know. So it could be any kind of correlations. Yeah, and then basically what this does to your set, it just broadens it a bit. So yeah. Yeah, one example that we had in mind is for coherent states, where basically the particle number is connected to the spin, and then you can actually determine this this delta explicitly. Yeah, the details are not very important here. Yeah, you could also do the same thing for the classical set. So again, we are now sure with, for example, 90% that our assumption holds. With 10%, we don't know what is happening. So yeah, we just can have any kind of correlations. And this will give us the full picture here. Using this, we can now talk about randomness certification. So we are describing a random number generator, so we actually want to know that we're actually getting some random numbers. And therefore, we will analyze this quantity here, this entropy. And basically, what is important here, it is a conditional entropy, and it is also conditioned on your hidden variables. So this means it's also random to some eavesdropper who might have more classical knowledge about the setup and the inner workings of the boxes that we don't have. And yeah, basically, you then want to lower bound this entropy and find the lower bound of this. Details, again, not super important as it. But what is important is basically when this is greater than 0, then you have some certified randomness. And this is equivalent of being outside of the classical set. So when you're somewhere here in this area, then you know that basically you have some random numbers which are also random to some eavesdropper. Okay, so also all of this so far heavily relied on quantum mechanics, and that quantum mechanics is true. So what we now want to do is we want to drop quantum theory and describe all of this in a more theory-independent way. And as also Marcus explained before, what we can basically do is we can look at these probability distributions, which we can just write as a Fourier series, since we assume that they are 2π periodic, and implement our assumption here by saying that our series has to terminate at 2j. This is actually corresponding to the same assumption as we had before. Yeah, the factor 2j comes because we are looking at the probability distributions and not the representation on the Hilbert space. But it would in the quantum case, this would lead to the same bound here. Yeah, there are different ways to derive this. The first one was either just looking at this 2π periodicity, using that you can develop this into a Fourier series. But there's also another way of arguing, which is more general. So this would also work for other groups, that you say, okay, actually this form of probability distribution comes from some underlying representation on some state space, which is not necessarily a quantum state space. And yeah, so yeah, you could use this theorem to derive the same form. Good. So then again, we will define now the rotational box set, the correlations from the rotational boxes in a very similar way as before. So you have those two correlators. And yeah, we just assume now that the probabilities, how they are created, are of this form here. And then we again give a description of the set in a different way. For this we use this lemma, which is in general true for trigonometrical polynomials of degree n. N is in our case 2j. And then with some calculations, you actually found the same inequality as before, which means for two inputs and two outputs, the two sets are the same. So the quantum set of the correlations from quantum mechanics are the same as for the rotational boxes. Which is a nice result, because this basically also certifies that now the randomness generation is also valid even if quantum mechanics doesn't hold. And yeah, so we could redefine the classical sets now using basically these the correlations from this set here. Yeah, so in upcoming work, I mean, Marcus already talked about this. We are now studying not only two input to output setting, but also continuous inputs, where we basically look at the set of space-time boxes and the set of quantum boxes, and we study those kind of probability distributions, either just saying, okay, they are of this general form, or if they have, or for the quantum case, they have to come from the Born rule. And as Marcus also mentioned, it's pretty trivial that basically the quantum set must be a subset of the rotational box set. But the other way around, and this is also worked together with Thomas Gelly, we found that for the case the j is 0, 1/2, and 1, they're still the same. But if you go to 3/2 or larger j, then there is a difference and there is a gap. Yeah, so the conclusion of my talk is basically that, as we've seen in this two input to output setting, the set of correlations that come from the rotational boxes are exactly the same as for the quantum case, which implies that also the randomness generation of is also secure against post-quantum eavesdroppers. And yeah, for continuous inputs, we will see a gap, which we can try to then study the underlying GPTs and see which implications that has. And yeah, so as a further outlook, we try to analyze different symmetry groups and also some other setups and other scenarios. And something that is very closely related to our setup described here are also speed limits, which would go beyond quantum theory. So yeah.
Thank you so much.